code and
อ่านมาด้วย So, as I was saying, the three-qubit code is not a complete quantum error correction code yet because the three-qubit code, it can only be used to correct either the bit flip or the phase flip. So, as seen from this one that I'm showing here is the three-qubit bit flip code, which can only be used to correct bit flip, as a phase flip would cause an undetectable error in this code. And
nice.
same thing goes for the three-qubit phase flip code,
Mhm,
which is here, this one,
mhm.
this one here. It cannot correct the bit flip code, but the short code is, let's say, an amalgamation of these two code. It's basically just these two codes just stringed together, so it can correct any arbitrary errors. Like is this one here.
I see. Okay, good.
Okay, so the topic of today's talk will be about the quantum Hamming bound and the stabilizers formalism, which uh, I have prepared a bit here, so it wouldn't be like the other time where I just come in and write stuff. This one I already prepared the writings here. So we'll first go through the quantum Hamming bound, which is a bound for a set non-degenerate codes. Right. So in quantum error correction, we're interested in three numbers, which is used to label the code. It's called the classification or just the code label, which is these three numbers right here, NKD. N is the total qubits used. K is the logical qubits encoded, which classically, this would respond to, I mean, this would correspond to the code dimensions. Here's just the logical qubit. And D is the code distance, which is not the same as the classical. Classically, the code distance is defined to be the amount of operations or errors that are needed to go from one code word to the other. If there are multiple code words, then it's the minimum amount of error. But
Uh,
since
okay.
one quantum error correcting code. There are some variations that cannot correct all types of error. We then change this definition into the max distance that can cause an undetectable errors. And when I say distance, that means that it's the amount of positions that are different from the identity, right?
Uh, so you're using density operator formalism instead of wave function. Am I understand that correct?
This isn't the density, it's just labeling the code.
Oh, um, mm, ah, sorry, but can you can you tell me again how you define distance? Is it a distance of a specific sorry, is it a distance between two wave functions or is it distance between I don't know two operators? How do you
between
define
two states, between two quantum states.
and what do you
So I
mean by
think that the question is how do you define the distance here? So I think in the perspective in Takla's perspective, he is thinking about the metric that you use to quantify this distance. But basically this is just how many bits do you need to flip or to change in order to I mean let's say how many error how many bit flip or error occurs such that your code cannot fix the error anymore. So distance is defined as so one unit of distance is one single error that occurs to your system, let's say.
Yes.
So let's say if you have a let's say just two qubits, if one of the two qubits flips, and then you compare that flipped qubits with the original qubit, you say the distance is one. So it's kind of the number of basic operation that you need to do in order to change from the original state to the final state. something like
Yes.
that.
Yes.
Yeah.
I
So let,
think.
let but so
Mhm.
let me comment a bit right now. So I think Atom, I know that it is not an easy task to prepare all this presentation, but I would say that it would be much better if you try um, to clarify all the term using technical words, but also explain clearly what it means, and also show um, some examples which would clarify the concept. So, for example, yesterday you talked about error correcting code, but you haven't actually shown clearly how this code can correct stuff. What happened when after the measurement, how do you fix how from that information that you get from the measurement, how can you fix the error or something like that? These points are not quite clear enough yesterday, right? And also the word like syndrome measurement is not something that you mentioned yesterday, or sorry, the day before. So all these things you should be more careful. You should try to um, present it in such a way that everyone feel that it's all clear what you mean. Okay. Yep.
Yes. Okay.
I
Okay.
think we also have to be fair to him because I think he has examples afterward.
Yeah.
I
No,
asked the question too soon. I'm
I'm
sorry.
writing.
no, what? Okay. So what I mentioned is just
Down here.
according to the first lecture the other day.
Okay. Yeah. Yeah.
Mm. Okay, please continue.
Okay. So, when just to clarify the word distance a bit more, when we're talking about qubits transformation, we usually refer to some matrix or some operators that are being done on qubits, right? So let's say we go back to the 3-qubit bit flip code. That one, classically, this distance is defined between, I'm sorry, this distance is defined as the difference, how many operations you have to do to go from one code word to the other. If you use that definition here, then the 0L here is the code word, which is just 000, and the other code word, which is 111. This one here, you need to do the poly X matrix 3 times in order to reach the 111 code word. So the classical distance of this code, it will be 3. Distance is 3. Because what I said earlier, that the distance is the positions that are different from the identity. I mean that it's these positions. Because when you write an identity operator, you write it as 1 tensor 1 tensor 1. And you just count up how many positions are different from 1. In this one, it's 3 sigma x right here. So that's 3, and that's the classical distance. But now, because the quantum distance is defined differently, it still is counting the positions that are different from 1, but it's instead defined as the maximum distance that can cause an undetectable error. And uh, this can be directly expressed in form of the faceflip because this is because the 3-qubit bit flip code, it cannot detect the faceflip. So just one faceflip using a single poly Z matrix will send the system into a different state that is undetectable by the code. Therefore, you can say that the 3-qubit bit flip code is a 3-1-1 code, meaning 3 total qubits, 1 logical qubits, and code distance of 1. All right. Now, the next example that I would bring up is the Shor's code here. The Shor's code here is a 913 code. So 9 just represents the total number of qubits. It's 9 qubits, and it's only used to encode one qubit of information. Now, the code distance is 3 because we got the minimal distance between code words here or any states is just 3. That will provide an undetectable error, which this one is the distance of 3 is actually equal to the classical distance because the source code can correct any arbitrary type of errors, right? And that 3 operations, it can be used using the poly-Z matrix thrice, as seen here. I've put the tensor 3 above here. Okay. Now that you know how to label the code, another another term that I would introduce in order to reach just explaining the quantum Hamming bound is the T, which is the amount of allowed errors here. All right. So T is defined to be the floor function of d minus 1 over 2. And why might that be, you might say? So you can imagine that you have two code words or more. Here I've just drawn 2, and this code word can represent 0, 0, 0, or just 1, 1, 1 right here. And the distance between it is d. So the amount of allowed errors before the state gets flipped into the other code word. So like if you start with a 0, 0, 0, and then the error moves the state into somewhere here, it will still be detectable as a 0, 0, 0. But if you start to go out of this circle, or like here, the state, it wouldn't be detectable as 0, 0, 0 anymore, and it will actually change into the other code word. So T is basically an allowed error that will leave the state still remain detectable. So sorry, I pressed the wrong button. So to derive the expression of T, we start with a simple inequality, which is just 2T must be less than D. This is because we can imagine 2 spheres here. That represents the distance of the errors here, just 2 spheres, and these spheres have the radius of T. You can see that in order for the spheres to not touch, 2T must be less than D. So we changed that into an equality by recognizing that the code distance can only increment by a number of 1, or it must be an integer. So we change that into an equality, then move sides around, and just use the floor functions because T must be a integer, right?
I actually have a question here.
Yes.
So you said D is the maximum number of errors that you can have so that it does not shift your logical bit, right? And you said that if, for example, like your qubit has been shifted more than T errors, it will flip. That means whatever this is, it has to be D, not D minus 1 over 2 floor,
Oh, okay.
right? Because if you look up, you in your example of quantum distance, you have one phase flipped in your in your physical qubit, and that flip your is flip your, what is it called, your qubit. Uh, no, that doesn't change a lot of things, but yeah. But my concern is still remain. T should be something else, like not the maximum amount of like undetectable errors, or maximum amount of error that does not flip your qubit, your logical qubit. Am I making sense? Mm.
Uh, Let me think about it for a bit. Yeah, yeah, it makes sense. It makes sense.
Mm. Maybe the answer is on the
Next
next
distance.
page.
No, I don't think next page has an answer because I just go straight onto the quantum Hamming bound here.
Yeah, but I don't
Like,
know how the book describe T.
actually, it actually is just described as the amount of uh allowed detectable errors before the bits get flipped.
But that's the definition of D, not
No, but D is say undetectable errors. Mm, maybe it's that D it would make sense if it's defined classically, right? Because the classical distance is the amount of operations you need to go from one code word to the other code word. But now it has become the maximum distance that can cause an undetectable error between states. Right? And I believe that this definition it came from the fact that some codes, like the 3-qubit code, it cannot correct an arbitrary type of errors. So
let's I think it's better to let's keep going. Maybe the answer will pop up. I don't know.
I'm
Yeah.
yeah, on this point I'm really not sure uh because in some literatures it actually says that the distance of the 3-qubit bit flip code is actually 3. But then there's something weird going on because if the distance is 3, then the 3-qubit bit flip code it violates the quantum Hamming bound, which it shouldn't because it's a degenerate code. So uh I've seen that in in later literatures, right, they use a distance of 1 instead. That's what I'm getting. So I'm continue for now,
Yeah,
and
sure.
if I have some answers, I will yeah yeah I will come back to here. At least I hope I do. Okay,
Yeah, no worry, no worry.
so the quantum Hamming bound is a bound or an inequality that degenerate code satisfy. So to recap from last time, a degenerate code is a code where you can't tell exactly where the errors has happened, but you can tell if an error happens and you can correct it. Those are called degenerate codes. A non-degenerate code is a code where you can tell where the errors happened exactly, like at what qubit does the error happen, and you can correct it as well, right? So the idea of the quantum Hamming bound is just that the amount of correctable errors should be less than the dimension of the state space. Because you will see later that the errors that are correctable they have to be orthogonal to each other. So I'm just putting that here for future reasons. So we can go on and count the amount of orthogonal correctable errors. So here's the quantum Hamming bound. It's in this yellow box right here. It's the sum. So we're basically counting all the I'm sorry. We're basically counting over all the allowed positions
Atom
for
M,
error.
Atom M, sorry to interrupt. Could I
Yes.
ask you that could I can I share your note to others? Uh,
Sure, if you will.
okay, okay, I will share to yeah, audience now. Yeah.
Yeah, sure. Mm,
Okay. Yeah, you can continue. Yeah.
okay. So we're just counting over all the positions that the errors are allowed. So we're going from 0 errors to T errors. And in each positions, there are 3 possible errors that can occur, the bit flip, the phase flip, and both. And that is where this term 3 to the J here is from. And then you must choose where the errors can happen. So we just use the amount of qubits, the amount of total qubits, and then just use n choose j, multiply that in. So you'll get that this is the amount of correctable errors in the code, and that should be less than the dimension of the state space here. And this dimension of the state space here is just 2 to the n. But then we have to remember that if an error occurs so that it actually overwrites the data, it wouldn't be correctable. So you need to subtract the amount of logical qubits there. So what you get is that the dimension of the state space here becomes 2 to the n minus k, right? So you get this Hamming bound here, which is an inequality I've shown. So such example would be the 3-qubit bit flip code here again, which is 311. If you plug those numbers in, you'll see that we'll get 1 is less than or equal to 4, which is great. It falls into the quantum Hamming bound, right? And the source code, even though the short code is a degenerate code, it still obeys the quantum Hamming bound, which you get here. 28 is less than or equal to 1028. Now, one thing about the Hamming bound is because the left-hand side is the amount of correctable errors, we want to maximize those. So for a quantum code, the higher the left-hand side is, we could say that it's more efficient or so, right? And that concludes the topic on quantum Hamming bound. Now, I would move
I have,
on. Yes,
before you move on, can I ask one question?
yes.
Uh, why is it 3 to the power of j instead of what is sigma
Or
x times sigma z? Is it identity or is it no, is
oh,
it sigma
these
y,
ones.
right?
Sigma x is the bit flip operation.
Yeah, and what is sigma x times sigma y? Is it
Wait,
something with sigma z, right?
wait,
Sorry,
did I write times? Uh,
no.
I
It was
I I were to write like there are three possible errors that can occur on any bit,
yes.
and those
And
errors are represented by sigma x, y, and z.
So the thing is, we need to be able to distinguish between the three kinds of error. So what I guess what you are saying is that you say that sigma, if there is a sigma x applying to a qubit and then followed by sigma y, you say that it is equivalent to apply sigma z to
yeah,
that
that's
qubit,
my
right?
concern.
But that is not what we want here. We want to be able to distinguish between these three cases separately. We want to know whether one qubit is subjected to sigma x or sigma y or sigma z.
Oh,
Because
just one.
yeah, or yeah,
At most
because
one.
we
It could be
want to know
zero.
exactly what is going on with the qubit because then we can fix it correctly.
I
Okay, so
see.
it could be that that single qubit could be subjected to sigma x and then sigma y, and that would be equivalent to be subjected to just one sigma z, right? That is totally fine, but you just need to know whether that one qubit is subjected
Uh,
to one sigma x or one sigma y or
I
one
see.
sigma z. If you know
Okay.
it, then you can correct it. So you need to be able to distinguish the three of them.
I see.
Okay. Yep. Okay. Please continue.
Okay. So I would move on to the stabilizer formalisms of error correction code. And well, I'll be sure to warn you that the stabilizer formalism, it's quite a mathematical topic, requires the need of generators and stabilizers and whatever those are. And I might not have enough time to prepare a good document on this as well because it's quite an abstract one. So what I would do here is I would introduce you the mathematical tools that are needed to understand the stabilizer formalism, and then try to link those mathematical tools to what's actually going on in the 3-qubit bit flip code and the source code, right? So in the first part, it's just gonna be some mathematics here. So in the stabilizer formalism, we're interested in the Pauli operators, which are these operators right here that I've written right here. Sigma y is just combinations of those two, right? And then I've also written the eigenvalues and eigenvectors of them here. So one thing that you notice is the sigma z here is just the standard measurement. You measure a 0, you get 1. You measure 1, you get -1. And that's it, right? So things that are special with the Pauli operators are these 5 things right here. Firstly, they are Hermitian, meaning that they represent some types of measurement, and they are unitary. That means that it also represents some evolution in the quantum space of the system. And the third one is just wrote it for mathematical reasons. They are idempotent, meaning that when you square it, they all square to identity, right? And the fourth property here, right here, I'm not sure if I'm going through this too fast or not. The fourth property right here, the commuting and anti-commuting property, this one is actually used to detect errors. So for non-identity Pauli operators, uh, they will anti-commute, meaning that if I is not equal to j here, poly I, poly j here. If I is not equal to j, then poly I, poly j is going to be equal to the negative of poly. I'm sorry.
Okay.
I'm sorry. Yeah, it has to be poly j, poly I. Here. Poly j, poly I here. Great. So why did I bring this property up? Because you'll see at the end that every code they have their own set of operations, that those operations are they commute with the code word. So meaning that if you put the code word in, when you measure all those operators, you'll get a 1, all ones. Now, if an error happens there that is undetectable error, those errors will anti-commute with the operations. So when you read those operations, what you'll get is -1. And you can use those as the syndrome measurement or just the parity checks that we've discussed earlier to correct back the quantum state, right? And then another property of these operators is when you measure using these Pauli operators, it actually splits the Hilbert space in half. It splits the Hilbert space into the +1 eigenspace and the -1 eigenspace, right?
Yeah,
So,
may I ask something that the condition 3, why it is
yes.
necessary,
Oh,
the condition T idempotent.
I put it there because in you'll see in a bit that the idempotent is used to calculate the projector. It's used in the circuit itself. So I put it there.
Okay, but could I ask that this is something like the properties of sigma matrix, Pauli matrix, right? But generally, uh, for example, other operators, it could satisfy all conditions if you don't use Pauli matrix. This is general for any stabilizer formalism,
Uh,
or it depends on using Pauli operator.
I'm really not sure about that because I haven't seen like any stabilizers formalism that they don't use the Pauli operators. Like yeah, because the Pauli operators they're easy to measure. So
Okay, okay. Yeah, you can
so then
skip
we
now.
have
Okay.
or is it wait, or is it not called idempotent? Is it called nilpotent?
Yeah, just for
I think it
footnotes
I think it's
here,
called
I think
nilpotent.
for Q-trait, we have a set of operators which satisfy all these conditions. Like is Hermitian unitary idempotent, and it has a nice like multiplication multiplication identities. Like you can write matrix 1 times matrix 2 equal to matrix 3 with some coefficients that you can look up on a matrix which is symmetric or Hermitian. I cannot remember, but I have heard of this. Yeah.
I'm really
Some
not
people
sure.
try to use this to study like tomography.
Okay. It has like all these nice properties, right?
Mm,
I'm really not sure
I
because
think
like
it's Hermitian for sure. Unitary, I cannot remember. But yeah, it's idempotent because we want it to be a projector.
is it called idempotent? I'm really not sure about that one.
Idempotent, yes.
I think idem is it called idempotent?
Idempotent, because nilpotent is a
Nilpotent is
generalization of
0,
idempotent.
right?
Nilpotent means that when you multiply it with itself for maybe n times, then it will become identity. And that
N
n can be
times.
anything. Yeah, it can be 2 or can be whatever. But idempotent is n equals to 2. So
Okay.
idempotent is like a special case of nilpotent.
Oh, special case of nilpotent. Okay.
I have one comment. So
Yes.
actually, if you have the first and the second property, doesn't that means you imply the third property already?
Yes.
Yeah, so
I
Yes,
to
yes,
point out,
yes.
right?
Yes.
It's nice to point out.
Yeah, it's nice to point out. Yeah, but yeah,
so
it does imply the third.
yeah, so you don't actually need to write that down, right? Or you can just say the third property without mentioning the first two as well, I guess. Right? Because if you
Is
have the
it
third one, that would mean sigma j is its own inverse. And okay, but in that case, it doesn't mean that it has to be
yeah,
its own Hermitian. Okay.
doesn't mean it has to be self-adjoint. Yeah.
Okay. But anyway, 1 and 2 implies 3 already, right?
Yes. Yes.
Mhm.
Okay. So from here, I would like to elaborate on the how the not really elaborate, but give an example of how Pauli operators they split the Hilbert space in half here. So it's on the next page here. So let's say you have two operators acting on two qubits as seen here. So poly z, tensor 1 and 1 tensor poly z. When you measure the poly z tensor 1 here, you can imagine the space of two qubits as some space like this, where in each quadrant, it's just a visualization, right, of the it's just a visualization of the four-dimensional space here. But you can imagine that each quadrant is the vector that is spanned by these states that I've written here. So the quadrant here, the pink quadrant here will be the span of 0, 0, and the same is true for every other quadrant, right? So when you apply the poly z tensor 1 onto any type state, it will split the Hilbert space in half, as in this top half this top half is going to have the eigenvalues of 1, and the bottom half is going to have the eigenvalue of -1. And well, you can split the Hilbert space again using another Pauli operator, which is this one, identity tensor sigma z, which will split it into the left half, which is -1, and the right half, which is +1. So it means that given a sufficient set of these Pauli operators, it can be used to specify the qubit states through this measurement, right? Okay, so when given a dimension of the state space, right? When you're given a dimension of the state space, if you want to identify a vector using these Hilbert space splitting Pauli operators, you require log 2 of those to identify a vector. This is because the Pauli, it splits the Hilbert space in half. So you can imagine if the dimension is the 2 to the n, you need n operators. Great. That brings me to the next topic, which is the Pauli stabilizers. The stabilizers are important, as in stabilizers, they are a some matrix that when acted onto a state vector, they leave the state vector the same. And yes, I wrote it. The global phase actually matters with this one. So some examples might be this one, which is poly z 2 times tensor 1. When you act that on 0, 0, 0, it gives out 0, 0, 0. And another example would be this one, which is an identity tensor poly z on 1, 0. It wouldn't change the state. And each matrix S, they have their own stabilizing states. Say S is called the stabilizer. And I believe that this psi right here. Oh wait, I just turned the page. Oh god. The state right here is called a stabilizing kit or a stabilizer state, which corresponds to the stabilizer S. So you'll see, as I said, that every quantum error correcting code, they have their own set of stabilizers. And normally, the code word is put to be the state that is in the simultaneous +1 eigenspace of stabilizers, meaning that the code word is commuting with every stabilizer of the quantum error correcting code, and the errors are just states that the errors are just operations that anti-commutes with the stabilizers. For example, you can use the 3-bit qubit bit flip code here, which it has two stabilizers here, which is written here. This one here. These two stabilizers give rise to, say, a family of detectable errors, which are these ones, which all anti-commutes with the stabilizer. So when you use the Pauli matrices to measure these states, if there is an error that occur, you'll get a -1 straight away, right? And you can use those as the syndrome measurement and go back and correct the states.
I have a question. I think I just missed. I think you have mentioned it before, but I miss it.
Yes.
What state is the set is this example is a stabilizer of?
Oh, it's the code word state, which is 0, 0, 0 and 1, 1, 1.
So it's stabilizer for both.
Yeah, it's the stabilizer for both. Because
Okay.
I mean, we have 3 qubits right now, so the
Okay.
dimension of the space is 2 to the 3, right? So to specify a state, like directly specify a state per se, you need three stabilizers. Or not really three stabilizers, you need three operators to specify a state. But here, I've only put in two operators. That means that when you split the Hilbert space, what you'll be left with is actually a two-dimensional Hilbert space, which is spanned by these two vectors right here.
Good.
Does it make sense?
Mm. So, well, mm, okay, maybe to extend a little bit. So if I have a superposition of logical zero and logical
Yes.
one 3-qubit
Yes.
code, um, would it would this superposition also have these two operators as their stabilizers?
Yes. Well, that's just because
Oh yeah,
these stabilizers they're linear, right? So you can distribute them over and it will still be a stabilized state. So a state like this, why is my pen not working? Here. State like this will also be stabilized. One other thing that I somehow forgot to put in this note is that the product of two stabilizer is also a stabilizer, right?
Mhm.
Yeah, that should make sense because, well, if you apply a stabilizer, it doesn't change anything. If you apply another stabilizer, it also doesn't change anything, right? So stays the same, right? So if we actually think about that, the 3-qubit bit flip code, it actually has multiple stabilizers. You can select any one of those products, right? Yeah. So you can use these two stabilizers to form more stabilizers there. And to build the 3-qubit bit flip code, you can just select any one of those products here. But these are just they're called representations of the stabilizers. These two here, they represent the whole set of stabilizers, which it's called the stabilizing group, right? So
Can I ask you to show more stabilizers in this class? Because the only one I can think of that is not here is sigma z sigma z tensor identities tensor sigma
yes,
z.
yeah, that one is also in this class.
Oh, I think that's all. We only have 3 stabilizers.
Yeah, we only have three because when you multiply these two, you just get the other three, and there's no more, right?
Yeah.
They are idempotent.
I thought you said
Yeah,
there were more
yeah.
stabilizers.
There are more. Like in the source code, there are more.
I see.
Like source code, it uses 8 stabilizers to form the covariant space, right? So it actually has a lot more there, which you can use. Yeah, but it's just not here because this one it only has 3. So you can select any 2 of the 3, and it will still work, right? Okay, so moving on. This one is about how you can actually measure the Pauli operators, right? So it's actually a continuation of yesterday that Atan Om talked about the state collapsing after the measurement, and I hopefully, this page will answer those questions, right? So to measure the Pauli operators here, the stabilizers that are there, we use this circuit right here, which after measurement, it leaves the state into this state, proportional to 1 plus or minus p psi, where the p here is the Pauli operator, any Pauli operators. So this circuit can be used to measure x, y, z, Pauli x, Pauli y, Pauli z. It's really up to the stabilizers that are used by the code, right? So when you do that, you start with a state here, the state here, psi, and then you put an ancillary qubit, which for those who aren't here, ancillary means a helper qubits. It means helper, right? It is a way to, I wouldn't say non-destructively measure the state, but it is still a measurement of the state, right? Which you can extract information from. So let's go through the calculation and see what this circuit here does to the qubit. So we first start off with the psi tends to 0. You apply a Hadamard here. The 0 gets split up into 1 over root 2, 0 plus 1 over root 2, 1. And then I'm basing this on an assumption that a control Pauli operators can be implemented, right? So this control P here, this control P, it will apply the Pauli operator to the state psi. It will apply the Pauli operator to the state psi if it is a 1, right? If the control qubit is a 1. Therefore, well, this state is a 0, so you don't apply it. This state is a 1, so you apply the control P operator to here. And then you use another Hadamard gate to split it. So 0 becomes this state here, which is the plus state, and 1 here becomes the minus state here. And then you arrange and expand a bit, and then you get this form, which is a general form that we're going to see. Now, questions might be, what does these operators actually do to a qubit, right? And we'll see. Oh wait, I'm sorry, we're not there yet. So after measurement on the standard basis here, measurement on this qubit is 0 qubit. What you'll get is that if the measurement comes out to be 1, the state is left in this state. So measurement comes out to be 1, it means that you measure the 0 state, meaning that the whole state, if you remove the 0, is left in this state. 1 over 2 times identity plus p times psi. And then if you're left with a -1, I mean you measure it and you get -1, what you'll get is 1/2 times identity minus p psi. Now we're on to the action of these gates. So here's my quick claim here, which is this operator specifically is a projector onto the plus or minus 1 eigenspace of P, right? So these plus or minus sign are, well, they're the same sign. So if it's 1 over 2 identity plus P, then it projects onto the plus 1 eigenspace of P. So, and I shall prove it in the next page right here. So I want to say that idempotent is just squares to be the same, right? So we first have to verify that this is a projector. So you square it, and then you get the same thing, right? This also works for if it's a minus, which I somehow forgot. Yeah, but it should be simple to fix. It's just throw in a couple minus signs here and there. So it has to be here, here, and then squared, which is this and this. So it is a projector. And
let me ask a little bit. Did you mention anywhere before that P has to be
Pauli operator?
P has to be Pauli, right?
Yes,
Okay.
P has to be
Okay,
Pauli
so
operator.
that is why it is idempotent. Okay.
Yes, it
Okay,
squares to
fine.
1. Yeah,
Well,
that's why I mentioned it earlier. That's Pauli operators, they do square to 1 because it's used here, right?
okay. But let's say that in principle, P can be anything as long as it is idempotent, right? So this proof just relies on the fact that P has to be idempotent, which is not very clear yet whether it is equivalent to a Pauli operators. But anyway, right?
Mm, I mean, there's the condition here that it projects onto the plus or minus one eigenspace, which means that the eigenvalue it has to be either one or minus one, right? But I'm not sure if there are other projectors other than the Pauli projectors. Not really Pauli projectors, but
Actually,
are there?
matrices are not projector.
Yeah, they're not
Hence,
projector.
mean you square and you get the same matrix. You square a matrix and that matrix gives you identity is called an involution.
It's
I
called an
just look up
involution,
terminology,
right?
yes.
Okay.
Involution. It's like evolution, but with in instead of
I
en.
involution. It's this one,
Involution.
right? Involution.
Yes. A
Okay.
matrix M is in an involution if its square is equal to identity.
Okay.
Make sense?
Yeah, that makes sense.
Uh,
Well, all projectors are idempotent, right? But Pauli matrices itself, they are involutions.
projector
Am I correct?
is let me look up. I don't want to just recall my. Okay, idempotent is bounded linear operator on the Hilbert space such that its square equal to itself. This is definition of idempotent. Projection is an idempotent operator such that its kernel is equal to the orthogonal complement of its range, which means um, you take the image, like the entire image, like all of the range of P of the your projector. You
Yes.
look whatever is orthogonal to this is in its kernel. And that's definition of projection.
Okay.
I'm not sure if that's like too mathematically technical.
I forgot what a kernel is.
A kernel is a set
Yeah,
of
remind me of that.
All the elements in your space that get mapped by an operator to a zero vector, to the zero vector.
Set of
Yeah, actually, I think the way, yeah, what Takara said is correct. So the word idempotent is, yeah, and nilpotent is are not quite correct. Yeah, Takara is correct. Is right. Now that I also help checking again, and yeah, I think he's correct.
okay. That is one of
ไบร
the
ท์ไบรท์
things
บอก
they
ว่ามัน
said.
เหมือนแกมมาไฟยังไงนะผมไม่เข้าใจอ่ะไบรท์พูด
อ๋อ
ผมอยากรู้เหมือนกัน
Yeah.
ใน string theory เหรอ
sure.
ใช่ปะ
Yeah, okay. First, actually, like Nong Adam says, like we require some property about P, the Pauli, but actually it has not. It can be anything that are satisfy like the commutation relation and anti-commutation relation that Atom shows like in the previous page. But in this case, people like to use like Pauli because Pauli is either commute or anti-commute. So it is like a lot simpler to talk about detectable error and undetectable error in this context. I think one simple example is that if the error commute with Pauli, like with the stabilizer, but you could say that we cannot detect it
Yeah,
because
it's an undetectable error,
yes,
right?
yes.
Yes.
Mhm.
Well, I said yes, it's about detectable and undetectable errors.
Mm.
Okay. So the next thing is that this operator here, it projects onto the plus or minus one eigenspace here, which I mean you can prove simply by just setting this equation right here, which is let the eigenvalues of the Pauli operators just be one and minus one. and I've used lambda plus or minus there. So when you apply this to any certain ket, because the Pauli operator are Hermitian, it has its own, what do you call it? Their eigenvectors span the whole space, right? So when you apply it here, what you get is that you can write any state psi into a sum of Pauli operators. Sorry, I mean a sum of their eigenstates. Yeah, a sum of their eigenstates. Then you could just apply that in and then expand out. You'll get this form here, which if the plus or minus is, if it is a plus sign, you'll get that after applying this operator, what you'll get is the alpha, is the +1 eigenstate. But if it is a minus, what you'll get is a -1 eigenstate. Right? So this construction is used to measure the Z stabilizers in quantum error correcting code, right? But well, the construction that I've shown you earlier, this one, it is a bit hard to implement because you need to implement a control Pauli operators. So I mean, I'm really not sure if it's that hard or not to implement, but I've seen it used. But a simpler construction would be to use the C0 gate itself, right? Here. So if you want to measure Pauli Z, what you do is just use a simple C0 gate and then measure the ancillary. If you want to measure Pauli X, you put the Hadamard instead of on the zero on the ancillary state, you put it directly on the psi state. So you also get the same result. Well, I've actually written the proof, but it's not here. I don't remember. It's yeah, it's here. Okay. Yeah, this one. You can actually go and verify that these two circuit with the control X and the C0, they're equal. But I mean, it is a bit long. So yeah, and you can also verify that the control Z, they're also equal, right? Go back to the note. Okay. So this scheme of measuring the Pauli operators, they can be extended to simultaneous measurements. For example, still the same thing. In the 3-qubit bitflip code, that one, it uses something called a parity measurement, which uses two Pauli operators at once. They are, yeah, they just use two Pauli operators at once, right? So you can just extend it to being this form. Just use the control set and then just link it up here, which is equivalent to just doing this, use a Toffoli gate. Right?
Oh, by the way, do you know what parity mean in this case?
It means whether the value of the two bits are the same or not. Right? Yeah, it's a number. It's
yes.
a 0, 0, 1. Basically, if the value of the qubit is 0, 0, or 1, 1, then the parity is, well, they're the same, so it outputs a,
Just has parity 0.
yeah, it has parity 0. Then if it's 1, 0 or 0, 1, then it has parity 1, right?
And is this the same as Hamming weight of a state?
Hamming weight.
Yeah, I cannot remember, but it's very close to parity.
I'm actually not sure what's, because like I haven't heard of the term Hamming weight before. Sorry.
Like you talk about Hamming weight bound, right? Hamming bound.
Yeah, I did talk about the Hamming bound.
Yeah. Isn't it related?
But
yeah, it's about a number of 1 bits in the case of bit strings.
Yes.
So for example, 0 has Hamming weight equal 0, 1 has Hamming weight equal to 2. But maybe this is not
Well,
related.
I don't think it is, because the parity, it just measures whether two qubits are the same or not. It doesn't actually count up the amount of ones.
No. It's different. It's different.
Oh, it's different. Okay. So these are the calculations of the, like, I mean, still, I don't really have a proof that you can extend it. I'm sure that there is a proof somewhere, but I just haven't found it yet. Let's just say that. But just to show you that it actually works, I've gone out and expand this one. So you can see that it's actually a parity measurement, and you can use the same scheme for any types of stabilizers, right? So firstly, you couple the ancilla here. That becomes the state. You apply the C naught here. Just flip if there's a 1, and you apply the second C naught here. And you can pull the zeros out, right? You can pull the 0 out here and turn it into some kind of entangled state. And well, you can write those states as a projector right here. So this state and this is the same form, right? And also this one, which you'll see that if you extend it to the 2-qubit space, this one is just P, right? This one is just P, and this is 1. So it is an example that it actually works, and it projects the, what did I write? It projects the state onto the +1 eigenspace, right? So with the projection, it actually answers Dan Ohm's comment yesterday that for a general state psi, measurement actually collapses the state, but it collapses into the state of the ±1 eigenspace of these Pauli operators, right? So it means that, well, if you can correct an X error and you can correct an XZ error, you can correct any type of arbitrary errors, because it will just project the state onto the ±1 eigenspace. Please correct me if I'm saying anything wrong here.
Sorry, I was in the middle of something.
Oh,
Yeah, please continue. Sorry about that.
does it make sense though to the ones listening?
Why you think is had something wrong?
Because I'm actually not sure, because this one it isn't written explicitly on most textbook. I just found this one on Arthur Eckert's, and I'm really not sure if this interpretation is correct or not, because I interpret this myself. Let's just so please correct me if you see anything wrong, right? So, well, now that you see that these Pauli operators, it can be measured, and it can be used to detect errors by measuring them and see that, well, it's a -1 or +1 if the value is commute or not. We can actually go back to the 3-qubit bit flip code and see that these generators that I've mentioned here, sorry, can't find where it's. These generators that I've mentioned here, right here, which is the stabilizers that are here, it actually corresponds to how the 3-qubit measurement is measuring the ancilla, right? Sorry if my words gets mixed up a bit here. So if you go back here, see these circuit, right, that are used to detect errors and to create the measure syndrome. This first block right here actually corresponds to the operator poly Z, and then 1, right? And this second block right here corresponds to 1 poly Z and poly Z. And those are the two stabilizers, the code word. So if there exists an error here, which, well, we're interested in the X error, you can see that these circuits right here will pick it up and reads as -1. And those can be used to correct the error later on, right? So hopefully, just hopefully, I have done explaining the stabilizer formalism to quantum error correcting code. So the next thing that I'm going to present that I said in earlier lecture, not really lecture, but like earlier talk, I'm sorry. Yeah, that there are algorithms that are more efficient than Shor's algorithm. And those are the 7-qubit code and the 5-qubit code, which can correct any type of errors, any types of quantum errors. Right? So because the measurement is quite complex, and I can't find a well enough explanation of why these stabilizers have to be this way, I'll just let you see for yourself that this is the stabilizers for the 5-qubit code. And well, the code word is extremely long, you know, it's like 8, it's 8, what do you call it, linear combinations of like 8 state texts. Yeah, meaning that. And here is the stabilizer for the source code, which, well, if you see this one, it actually represents each block, right? So the first two, it represents the parity measurement from the first block. This one represents the parity measurement in the second block. This one, the third, and this one measures the phase, overall phase of each block and compare the phase of each block. And that way, these stabilizers, it actually just represents the short codes in general. And said that the stabilizers can be used to specify vectors, or it splits the Hilbert space in half enough times. The short code is described by 8 stabilizers acting on 9 qubits, meaning that you still have two states left for the code word, right? This one is also the same. It's the 5-qubit code, which is provided with 4 stabilizers here, which means that it also leaves 2 vectors, 2 states that are can be used for the code word. And if you want to detect the measurement syndrome, you just use these stabilizers and see if they commute or anti-commute. Then you can use a lookup table, which I haven't written here, but it's actually in Wikipedia. Yeah, you can look those up and then just correct the errors back to its original state. So that would be the end of my talk for today. Thank you for listening. Right.
Yeah, thank you.
Any questions?
Yeah, could I ask that is there something that equivalent between Charles code and 5-qubit code here? We can something right if we have Charles code first and then translate to stabilizer code later. It have something like that.
To reduce the source code?
It can be something like equivalent something.
From what I've seen, the source code and the 5-qubit code is it is discovered independently and doesn't really use the short code to reduce it down. Well, I mean, there's actually, well, I can't really answer if there's a way to reduce it or not, but I've seen that in, I don't remember, LiDAR's textbook, he does mention that you can find a stabilizer for some space for some code word. Like there's a method to generate these stabilizers using provided code words, or you can go from the stabilizers to code word as well. Yeah.
Yeah.
But that's as far as I know. I can go read up on this later. Yeah, if you want me to like read whether the 5-qubit code can be generated for the short code or not, yeah, I can go and read that up later.
Yeah, I think there should be a map, but whether or not it will be meaningful, that's another story.
Yeah, but whether it's interpretable, whether we can interpret the map or not, that's another story. Yeah. Well, haven't I haven't found a good interpretation for the 5-qubit code yet.
Do you have you claimed here that 5-qubit code is the lowest possible?
Yes.
First, like what you mean by lowest possible, and second, do you have like some idea of how this is proved?
It's lowest possible according to the quantum Hamming bound.
Because D is equal to 3
Yeah,
minus
so yeah, we set k to 1 and d to 3 and solve the inequality, and then you'll see that 5 is actually the lowest possible here.
Let me see. Hamming bar.
Where is this degenerate? So
Maximum size.
Again, why you use K to be, I cannot follow. K is equal to
amount
1, yeah?
it's the amount of logical qubits
Okay.
that you want to encrypt, right? So this is just using only 1 qubit.
Hmm.
So
Can you show me the Hamming bar again? I would like to write.
Yeah. Could you like this an example of okay. Could you
now that I
repeat?
now that I think about it, I'm really not sure if it violates the Hamming bound or not. Let me check. Where is it?
Is
Before
in a
this.
yellow box?
Yeah,
Yeah.
this one. So it's gonna be j equals 0 to t is 3 minus 1 over 2. So that's just 1, isn't it? That's just 1. And then right to j. Then there are 5 possible positions for errors, and then j. So, I mean, it is a degenerate code. I think 2, 5, 3, 1, 5, 1. But 3, so it's just 1 plus 15, right? So that's 16. And the amount of correctable, the amount of state space, right, is 2 to the 5 minus 1, which is 16. So we get 16 is less than or equal to 16, which, I mean, it is the amount of correctable errors, right? So correctable error is 16, and the dimension of the state space for the errors is 16. So it's the most efficient, right? Yeah. So it's the lowest that you can go, because any higher than this, then well, you're gonna violate the Hamming bound here.
It's saturate the bound, right?
Yes, it saturates the
Yeah.
bound.
Okay. So it's the meaning of the lowest possible because it saturate the bound.
Yes.
That's right.
Yeah,
Okay.
it's I can't think of that word, saturate.
Saturate.
Yeah, it saturates the bound, right?
And you can have something like 7-qubit code and have separate throughout anything, right? Yeah. What is the the special of 5-qubit code now?
Uh,
So can I
like
help? It's kind of the most efficient way, right? The most efficient way that you can make the error correcting code, because you don't want to get too long error correction. You don't want to get too long code, but at the same time you want the amount of code that is enough for you to be able to fix all the error. So 5 is that magic number here. The shortest code that can fix all the three possible errors according to that act on one single qubit, right?
yes, yeah,
Mm.
shortest code, yes.
Okay, but it depends on the number 3, right? If it changed to answer number
Yeah, if it
5,
changed to other
it may
numbers, then it
change.
wouldn't be 5
Okay.
anymore.
Okay.
Yeah, but what from I've seen, it seems like it's special because as said earlier, like it's special because the code distance is the same as the short code, and it's kind of a reduction, but there should be a map, but I'm not sure if that map makes sense or not. Yeah. Uh,
So my question is it unique, this 5-qubit code?
is it unique?
Yeah.
Mm, I wouldn't say it's unique because this is just 4 of its generator. I mean, you can take like multiply these two generators and then sorry, stabilizers, right? You can multiply these stabilizers and
Yeah,
then
get a
get
new
another
one.
one, right? Like
Right.
I'm not
Okay.
sure if that's ZX. It's probably like IY, then 1, right?
So let's say it is the same, it is unique up to global phase, something like that, right?
Unique.
Up to, let's say, up to unitary transform, in a sense. Because
Mm,
like you can have these 4 stabilizers, but then you can kind of apply some unitary which transform this 4 stabilizer to a new one. But in a sense, it kind of preserve the symmetric structure of the stabilizer, I guess.
Yeah, you can do that. You can transform from one stabilizers to the other. I mean, Pauli operators, they are unitary, right? So when
Mm,
you multiply them, it will it will represent some unitary transformation. And
mm,
because when you multiply 2 stabilizers, you get another one,
mm-hmm.
and then you can just swap this other one in.
Yeah.
So yeah, I would say it is unique to transforms.
Yeah.
Transformation that preserves the state vector
Mm-hmm. Mm-hmm.
or preserve the covert.
Actually, like you can change the code word. You can transform code word together as well. Like if you conjugate everything by unitary with the same unitary, then like it's the same equivalence code but written in different bases.
Yeah.
So yeah,
Yes,
this is
in
unique,
different
but up
bases.
to at most this is unique up to unitary transformation.
Yeah, agree.
You can,
So what's
yeah,
next
but
for you? Oh,
measuring like IY, I'm really not sure how you could do that. I mean, you could use the phase shift gate. I think that works. But I'm not really sure how you would implement it. So it could be reduced down to like some simple Hadamard's and C naught.
What do you mean by that?
Because like if you multiply these two, right? Like multiply these two stabilizers to get another one. I believe they get another one and then use that another one to substitute back, then there'll be a relative phase of I and minus I that you would have to measure. And I'm not really sure how you would convert that into a circuit form, because there's a phase factor there with the I. But I guess you can use the phase shift gate. I'm really not sure about this. But yeah, I think it's just more complex, so people just don't use it. Yeah.
you mean to implement sigma y?
Yeah, to implement sigma y and then times I and have it be the same thing as like doing
Did notice.
1/2 yeah. I'm not sure if this how this implementation would work, right?
Mm, it will be a good exercise. You should try
Yeah,
to.
I'm gonna try this.
Oh, no. I think you can do it with like not sigma x, sigma y. Sorry, sigma x, sigma z, and not gate, and maybe c not. No. I think it's like not part of my sigma x, sigma z should give you you should be able to get this sigma
Like,
y. I'm not sure.
like this.
Anyway, it's thank you um Egapong to that for inviting me here. But right now I am a bit tired because if you can see it's dark there. It's getting dark. It's 10 p.m. now for me.
10 p.m.
Yeah, but it's relatively bright for 10 p.m.
Yeah,
because
it's
it's
really
summer.
still really bright, right?
Yeah, 11 a.m.
Here it's
Okay.
11 a.m. Yeah.
Yeah, maybe I'm not sure that Atom, do you have something next and that maybe you continue, yeah, or the direction, yeah. If not,
Like
yeah,
in the future, like what?
yeah. I
Uh,
will go to Japan about 2 weeks. Yeah, maybe we discuss later. But yeah, might be if possible, yeah, about having like yeah that in the paper or maybe continue in that book about fault tolerant quantum computing, something like that. Yeah,
yeah, sure.
yeah.
I'm
But
gonna go
but
study those.
you have your plan? Do you have your plan?
Uh,
Maybe might be.
I mean, I could go read on that paper on the quantum Hamming like bound for degenerate codes, because
Hmm.
I still haven't read it fully yet, right?
Hmm. Yeah,
And well,
but
there's
you
like
okay.
a topic on low density parity codes, and but I'm still not sure if that topic is still active or not.
Yeah. But I suggest that if you continue in that book about fault-tolerant quantum computation, you might be understand more about implementation more. Yeah, it might be good in that direction also.
Yeah,
Yeah, maybe we
sure.
discuss later, and yeah, maybe
Okay.
the next talk might be yeah after 2 weeks later now from now. Yeah, it depends on your progress also yeah ไม่ต้อง
Okay.
กดดันนะโอเคค่อยๆไป
Like I
any
still haven't
comment more yeah okay
I still haven't talked about like the general properties of what makes quantum error correction possible in the first place, which those are the condition like so I will just give a quick one here. Like if let's say I and J is a code word, then like I then error, like any independent errors here, E and F here must be orthogonal. So like there's like these conditions littered around which I'm still yet to fully understand. Yeah.
mm,
And I
yeah
might have to go read up on that. And if anything goes according to plan, that would be the topic of the next talk, if there is one. Right?
yeah okay okay
Okay.
okay
Yeah. Is
for
that
today
good?
yeah thank you everyone yeah okay very good
Yeah. Thank you
ข
everyone
อบคุณ
for
ครับ
listening.
ขอบ
Thank
คุณครับ
you.
Okay. Thank
Thank
you.
you.
okay thank you very much เจอกัน
ครั
นะ
บผม
ครับสวัสดีครับ
Okay.
ครับ
Bye
ส
bye.
วัสดีครับ
Oh, have a good day, not good night.
Jay,
I am night
good night
also
for you.
I like to sleep now yeah
Thank you.
ขอบคุณ
Yeah.
ครับ
ครับ
Good day.
บ๊ายบาย